Hello. Good morning, everyone. Welcome to the AstroSat proposal preparation webinar. And that is this is the cycle A012, that is announcement of opportunity 12 cycle, which is going to commence soon. So the advertisement is also now released from ISRO and ASSC team. So there will be two speakers for today's workshop. One is Dr. Yashpal Bhulla, and the second speaker is Dr. Divya Rawat. And these are the postdoctoral fellows working with AstroSat Science Support Cell, and they will explain the procedures and requirements which are necessary for a good proposal preparation with AstroSat, and with having lots of expectation towards seeing a good kind of proposal, we are hosting this webinar for today's workshop. With that, I would like to request Dr. Yashpal Bhulla to start his presentation.
Yeah, thank you, Jayashree. Okay, let me share my screen. My screen is visible for all? Jayashree, my screen is visible? Yeah. Hello, everyone. Welcome to the webinar on AstroSat proposal preparation. I'm Yashpal Bhulla. So, okay, AstroSat is first Indian multivalent astronomy satellite. It carries a payload of 5 different scientific instruments for multivalent observation. Like in this plot, all that 5 payload, like SPC, SXT, CZTI, SSM, and UVIT is mentioned clearly. So, since its launching, ISRO has periodically released the announcement of opportunity and call to the proposal for national and international student, researcher, and a person who belongs to astronomy community to observe the particular source using different AstroSat instrument. So this time, present days, ISRO has announced a AO12 cycle, which will be start from the 1st of October 2022 till the 30th September 2023. The proposal for this cycle is going on. It was started from the last month, 25th of January, and the last date for submission of proposal is 10th March 2022, 3:30 p.m. The allocation of observing time on AstroSat is quite similar as previous one, AO11. This is around 55% for Indian observer, Indian student, scientist, and researcher. And for international, it is 20%. Yeah. So next is we have the few online tools for successful proposal. This proposal, I requested two proposers strictly follow these tools. The first one is the scientific justification. The scientific justification is limiting to 4 pages. And in the scientific justification, proposer should describe the scientific background, target of interest, as well as the motivation behind the proposal, motivation behind the proposed. To add with this more, in the scientific justification, proposer should add scientific aim, what will be the aim for that proposal, and the selections of target, as well as demonstrating scientific feasibility with estimate of signal to noise ratio. And expected flux count rate during the observation should be mentioned. It should also be justify the feasibility of requested observing time. That requested observing time is basis on the result of exposure time calculator, AVIS tool, or the simulation tool. That simulation may be spectral simulation or temporal simulation. Instead of this, I would like to add one more basic information which could be in this scientific justification. If the source data is which proposer should proposer trying to propose, the data is already available on archival, and for new observation proposal, proposer should explain why this science case requires. It is must to report on previous successful AstroSat proposal by PI, if any, and also provide the status of observation, like example, like whether the observation is not published, or the data analysis is going on, or the quality of data, or on that particular source already publication from AstroSat is there or not. So these all important things should be added in the scientific justification. Okay. Next, we have the technical justification. Technical justification is limiting to only for 2 pages. In the technical justification, firstly, proposer should add the target visibility. This target visibility can be described or verified by the ASSC output tool. This ASSC output tool verifies whether the source is visible in the AO12 cycle duration, or source is visible in AO12 cycle duration. So in the technical justification, proposer should also add the primary and secondary instrument. Suppose someone has a SXP is primary and XPC is secondary, it should be clear in the technical justification. And it is mandatory to check each target requiring UV observation for safety concern. Suppose someone is proposing for very bright UV source, or the source which is in the field of view of UV observation. So it may affect the component, or may affect the filter or damage the filter. So proposal is mandatory. It's mentioned in the technical justification because of the safety concern. So instead of this, in the technical justification, proposer should add the selections of filter, sound noise ratio for the requested exposure time, and also for detail of time constraint. If the proposal is time constraint, then detail should be added. For example, for time constraint is like the coordinate observation with other observatories, like a monitoring duration and monitoring frequency. If there is trigger criteria for a APO, these things should also be mentioned in the technical justification. Yeah, next we have the types of proposal. So we have the 4 different types of proposal, like a regular pointing, monitoring proposal, anticipated TO, as well as AstroSat long-term key proposal. So first one is the regular pointing proposal. This regular pointing proposal either time constraint or without time constraint. If this is the without time constraint, that it is quite simplest to propose. For this, in this proposal, proposer can propose one or more target requesting one pointing per target. It means like in a particular, in this proposal, proposer can add more than one target, like more than one sources. And if regular pointing is time constraint proposal, then the scientific justification should be stronger than a without time constraint. This is because of the if source. This is because of the time constraining to ease of scheduling by the ISRO. And for each time constraint target in proposal, only one observation will be made. Means you are proposing for 5 or 6 different target, different sources. For each one, only one will be made. But however, if the multiple time constraint may be given, that is because of the ease of scheduling also. If multiple observations are required, then we will prefer to proposal write different or separate proposal or the monitoring proposal. Yeah, to next, we have the monitoring proposal. The monitoring proposal, proposer can request monitoring observation with a minimum interval of 3 days between 2 consecutive observations. Like in the monitoring proposal, for one particular target, proposer can request for the 2, 3, 4 or many observations, but each observation gap should be minimum 3 days. Will be minimum 3 days. So multiple observation is possible for single particular target in the monitoring proposal. And in this monitoring proposal, all observations are identical, and like the exposure time and instrumented configuration. Like the proposer are requesting for one particular source, and 5 different observations. The 5 different observations should have the same time exposure. Like 10,000 is for the first observation, 10,000 for second, 10,000 for third. And the instrument configuration remain same. Like for the first observation, proposer have the leg species, the primary, and for second, third, fourth, that will remain same. Next, we have the successive observation make not equally spaced. Means the proposer I have mentioned here minimum 3 days, but the gap will not be same for all the observation. So it depends upon the scientific goal. Proposer should be constrained on the mission operation. So be careful, proposer should add the strong justification needed. One monitoring proposal recommend only one target, not like the regular. In the regular, we can apply for many observation, propose for many observation, but in this case, only one target is there. Instead of this, there are 2 additional inputs required. One is the number of observation, and the second is the interval between successive observation in days. So now one thing is important in the monitoring proposal time, what will be your total requesting time? So like you are proposing for the 5 observation and one observation may be at 10,000 seconds. So your total exposure time should be 50 kilosecond. 50,000 mean 5 observation into 10,000, 50 kilosecond total exposure time you will propose in this proposal. Next, we have the anticipated TO proposal. It is third type of proposal. This type of proposal only consider when interesting astronomical event is foreseen. But the exact timing for that event is unknown. No idea, but we have the probability, but no exact idea about the event when it will be occur. So next in this proposal has to provide the triggering criteria and probability of occurrence, duration of trigger, and provide relevant justification. This anticipated PO proposal not allow to follow up observation in the same proposal. As well as proposer should have strong scientific justification because of it will not have expected time, so it can be interfere in other observation schedule. Instead of this, we have the 3 additional inputs required for this. First, how is the triggering criteria met? That is a very important concept. For example, the source flux crosses certain threshold. Suppose the flux of the source is you are providing the particular barrier for the flux. If the flux of that source is cross that barrier, then you want to trigger it. Then the user can trigger it. And instead of this, black hole X-ray binaries make a transition to a particular state. You want to get the data, you want to get the observation in a particular state. So then the proposer can trigger it. Estimated probability of occurrence. It should be 0 or 1. You should have the probability of occurrence of the event, that event will be occurrence 100% or 0. That should be mentioned in this anticipated TO proposal. And expected duration in the event should be in hours. And that can make sure how long is the trigger duration estimated. That would be easy for scheduling as well. So this is the last one proposal, AstroSat long-term key proposal, ALTKP. For this proposal, the length of this proposal limit to 6 pages. However, in other proposal, the length should be small. So this is for the target for specific science problems and demanding long-term observation. So we can say this particular proposal is used for enhance the scientific output, which may not be possible already available data on archival. So the preference will be given to this proposal only which will have the wider interest in astronomical community, and preference will be given to the proposal who are utilizing simultaneously multi-wavelength observation capability of AstroSat, who are proposing for multiple payload will be given to preference. Okay, so next there are few additional inputs. Definitely the length of the proposal is long, so it should have strong scientific justification. Instead of this, scientific merits by giving example of the previous similar or monitoring program of other observatories which already on archive. This will help to or benefit to similar kind of information provided. Proposal should have provide also in the proposal should have also include their expertise in the analyzing of AstroSat data and the status of the requesting observation mentioned clearly. For example, if any previous accepted proposal and publication based on them. So this type of proposal encourages to lead the project, especially for PDFs and young researcher. Yeah. Next, we have the observing efficiency for different payloads. We know that AstroSat have these 4 major payload, and each payload have particular observing efficiency. Like for UV, it has observing efficiency 15%, but this 15% for full field of view or field size or more than the field size is 250 cross 250. Like this 250 cross 250, then the exposure time per orbit will be more maximum. Okay. Similarly, for the ASSC, the observing efficiency is 25%, and for LEX-PC and CZTI is observing efficiency is quite similar. It is around 45%. So, observing efficiency. Why observing efficiency is important? That is because to requesting or ask the observing time in your proposal. We should be careful to ask the observation time. That can be estimated by this particular equation, by this particular formula. Observation time by the observing efficiency equal to stay time. Okay. I'm giving example for this. Like, suppose we have the SXT is a primary instrument, and the observation requested time for the SXT is 10 kilosecond. Then the total stay time will be, we can easily find out the total stay time like this form. By this formula, observation time is 10,000, and observing efficiency for the SXT is 25%. So 10,000 by 25%, the stay time will be around 40 kilosecond. Obvious, 10,000 into 100 by 25, 10,000 into 4, that will be 40 kilosecond. So we will have the stay time 40 kilosecond. Now we can easily find out the observation time for LEX-PC and CZTA because we have the stay time. For LEX-PC, stay time is 40 kilosecond. Observing efficiency is 45%. So 40,000 second into 45%. So it will be around 80 kilosecond observation time for the LEX-PC and CZTI. Similarly, we can find for the UVIT. UVIT has 15%. So 40,000 second into 15%. So it will be around 6 kilosecond for full field of view of UV. This is the observing efficiency for different payload to help you find out the observation time for particular instrument. Yeah. Next, we have another important concept is the relative angle. All the payloads on AstroSat have angle between payload bore side and body roll. All these angles are mentioned in this particular table for UV, SXT, LEX-PC 10, 20, 30, and mean LEX-PC angle is there, as well as the angle for the CZTA. Now the thing to know what is the payload bore side and body roll. So payload bore side is the axis which passes through each payload, and body roll passes through the center of center of gravity of satellite. Instead of this, we have roll, pitch, and yaw. Roll, pitch, and yaw are the terms representing the orientation of the satellite. Now, the important question, why to understand the relative angle is important. Why relative angle is important? This is because to know the primary and secondary instrument. Suppose one is your primary instrument. Now you should have noticed your secondary instrument is under the field of view or offset. So this relative angle will help you to find out your primary and secondary instrument. So if the source supposed to be out of SXP field of view, then the proposer should use PC mode data as a secondary instrument. If the proposer consider as SXP as a primary instrument, then the proposer can use FW mode data because of its better time resolution and the scientific goal in order to reduce pileup. In such as SXP, to use the FW mode data, SXP should be the primary instrument, even if SXP does not serve primary science. Yeah. Next, we have the AVIS online interface. This is very important to use to keep the AstroSat visibility period for observation of a target of interest. This link is providing here to move at particular page on ASSC website, and this AstroSat visibility calculator, it helps us to verify whether the source is in the particular AO12 observation. The visibility of source is available in AO12 observation. Suppose I am taking example here. There are 3 columns: target name, RA, and DAC. In target name, I put the one of source GX5-1, which is Z-track, neutron star, low mass X-ray binary neutron star. While I will put the name of source, it will automatically takes RA and DAC. And next, I will put the start and end time, which I use for the whole AO12 observation from the beginning of the 1st of October 2022 till 30th September 2023. Then I will tap on the AO12 period and generate. While I will tap on the generate, I will get the 2 different output. One is the table and another one is the plot, like this. This is the plot which we have generated from the AVIS tool. In this table, we have find the observation duration for LEX PC, which is in the red color, SXP in the blue, and UVT in the magenta color. In the x-axis, we have the in the y-axis, we have the kilosecond per day from the onset of the search of the angle, from the beginning of the AO12 cycle, at what time we can find our observation. So this kind of observation or this kind of plot will help us to ensure that the proposer should be time constrained or not. For example, in this plot, there are a couple of time interval where the data is not available, where the observation is not visible. So be careful and mention carefully these time slot in proposal, otherwise proposal may be rejected. Instead of this, we have one more example. This is the Blazer 3C 273. In this plot, it is clearly mentioned there is no visibility in this search duration in the AO12 cycle duration. So this is quite important to generate this tool to check the availability of data or not. So if your science case required time constraint, ensure that the time constraints are covered by the visibility windows. Okay. Yeah, next we have AstroSat payload receive different exposure per orbit. Okay, one thing is there, we are easily looking, we can easily check that for the LEX PC and CZPI, the observation time is quite longer as compared to SXP and UV. This is because of this very beautiful picture provided by Dipankar and Jayashri. In this picture, we can easily check The SXP and UV is only the data only can be observed in the orbital night. The data or the observation not beyond to the orbital night. However, in LEXPC and CZTI, the observation can be visible beyond the orbital night. So that is the reason we have the long observation for the LEXPC CZTI instead of the SXP and UV. SXP and UV can observe only during orbital night. And another one more thing, all instruments are switched off during the South Atlantic Anomaly Assay region. For UV, there is an additional overhead of switching on after the orbital night and switching off before orbital night ends. However, in SXT doesn't undergo such an on-off sequence. Now, next we have the LEXPC simulator. Yeah, so this tool is used to propose for the scientific justification is based on the temporal properties like coherent pulsation of pulsars and power density spectra or quasi-periodic oscillation from black hole neutron star sources or periodic and aperiodic variability light curves. This simulation tool creates the event file which we can use as a regular event file, or that event file is much compatible with the Formate LEXPC software that is available on ASSC webpage. This generated event file from use tool to create the simulated energy dependent light curves, power spectra, energy and frequency dependent time lags. To compile this and to find out this event file, we have to compile this code. For this code, gfortran is required, and simul.f code file is already available in this tool, and libc-fitsio.a library file keep in such location, and the output file, which can be executable for the further files. So there are two input files is required to run this code. First is input underscore fact underscore spec file and input underscore simul. Then we use this command to run and get the output simul underscore level 2 event dot fits file. In this two different input files, input fact spec file and input simul file, we have different parameters. We have different files available for this. Like in this input underscore fact spec file, we have the source spectrum fake file, and for the background we have backspec.fake file and response file lx20v1.0.rsp file, and we have mentioned here we are using for the number of proportion counter for event file simul underscore level 2 event fits file. Now for the input underscore simul file, we have put the basic inputs that we have. For that we have used the example like Maxi JS 1659152 black hole candidate. So we are using the exposure time 5000 seconds, that is for the simulation expected exposure time here, and we use the frequency of QPO in hertz 4.6 hertz. That frequency we have we took from the literature from any observatory, and the width of QPO in hertz 0.25 and RMS of QPO is around 0.06. So the photon index of power law continuum for power law spectrum is we keep it 1, and we took normalization of power law continuum is 1 minus 4 10 raised power 4 for this simulation. Now after that, what file we will get, and we to check the exposure time is sufficient for data set, and to check the simulated QPO is available in our simulation, we have used two different commands, and we are using this for the 15 to 20 kilo electron volt energy range. So in the first, we will use the lag spacing underscore find underscore frequency lag. That is command minus L 0.01. Minus L represent to the lower range or lower limit for the frequency, and H, which is a higher limit for the frequency that we have taken, it's 50.0, and frequency which we supposed to be and which we have from the literature 4.6. And we are using for PCU1 and any input file. In any input file, we put the energy range 15 to 25 and then give the event file simul underscore level to event file file. To run this command, we will find one output which name is 1po underscore level to event file. In this file, there are many columns will be there. So this file we will run in the GNU plot. So this command plot, this file U3:8. Okay, that 3:8, because 3 is represent to the frequency and 8 column is represent to the power, WL. After run this command, we will find the plot where we can check our simulation result is result is similar with the in literature result or not. Instead of this, we have the another way to find out the QPO, that is to generate the light curve. LXPC underscore make underscore light curve. Used for PCU1 and the bin time is 1 second, and again using for any input file and level 2 event files. So by this we can generate the light curve, and that light curve we can use it for the post spec and to check the whether our simulation is quietly similar with the literature or not, or what we expect from the data. So now this kind of simulation will help to understand the exposure time, what exposure time we are requesting in proposal. So I have done this for two different exposure time. One is for 15,000 and one is for the 2,000 second exposure. So I have seen while I was using 15,000 exposure, I got the frequency is 4.6, which is similar with the 2,000 second exposure. But what I have found, the error bar of the frequency in the 15,000 is 0.05. However, the error bar for 2,000 second is quite high. It is around double. It is twice of the 15,000 second exposure file. And the width is around 0.41 with the error bar 0.19 hertz. But in this case, the width is 0.18, but again, error is quite high. And we got the quality factor is around 11.3, it's around 11 and 7 sigma. But in the case of 2,000 second exposure, it is unable to constrain 1 sigma, and error on normalization is 0.6. Okay, so we can easily find out in which time exposure we are finding much precise and prominent result. So this can help us to give the request time in the proposal. Suppose I am getting the nice result in this time exposure. I can't, and proposer can't put or keep 20,000, 30,000 second exposure, can't demand for more than this unless the proposer, otherwise the proposal can be rejected. So this is the LXPC simulator which I have explained. Instead of this, there are few other tools which Dr. Divya Rawat will explain. So I am concluding my talk here. Thank you.
Thank you, Yashpal. So I will request Divya to please present her slide. And I will request all the participants to take a note on their questions. So the questions will be discussed after the presentation. Thank you. Is it visible? Yes, your slides are visible.
Okay. Hello everyone. Welcome to the webinar on the AstroSat proposal preparation. My name is Divya and I am a AstroSat Science Support Cell postdoctoral fellow working here at ICA. Today in this talk, I will explain about the various UVIT safety checks tools, and using the test examples, I will demonstrate the usage of these tools online on downloadable scripts. So the first one is the UVIT Bright Source Warning Tool. The Bright Source Warning Tool gives a list of all the bright visible stars in the field of view.
Divya, sorry to interrupt. Kindly minimize the presenter view. Thank you.
Okay. Wait, then I have
Yes,
to.
please go ahead.
Yeah, wait, then I have to restart maybe.
Hello. Yeah, your slides are now proper. Please go ahead. Divya, are you there? Hello.
Okay, hello everyone. Sorry, I shared the shared the slides in the wrong mode. So the first tool is the bright source warning tool, which gives a list of all bright sources that are visible in the field of view of the given target. And it tells whether the proposed source is safe for the UVIT observations or not. And this is one of the mandatory tool if a proposer is proposing a UVIT observation. And here is the link to the tool, and all the links which I am going to provide in the later slides and which Yashpal has provided are there in the ASSC web page. So here I have taken the test case. So this link will direct you to the bright source warning tool, and here you can give the inputs for the target of interest in the equation coordinates. You are supposed to give, the proposer is supposed to give the RA and DEC, the right ascension and declination angle details of the source in the format of hours, minute, second, and for declination it's degree, minute, second. And here I took the case of test case for the source HT 226868 and chosen the primary instrument as UVIT. In the coordinate field, the user is supposed to provide, yeah, as I said, RA and DEC. And while I generate, if you submit this job, you will get this output, and here's the output. That's how it looks like. So it says that the source is not safe for these filters, these UVIT filters, and this output the proposal should submit while submitting the proposal if one is proposing for the UVIT observation. Then next is the UVIT visible FUV and NUV filter checking tool. It is a tool to check whether a field can be safely observed with the UVIT, Viz, FUV and NUV filters. The UVIT is not designed to observe very bright sources, and the presence of a bright source in the UVIT field of observation can cause bright object trigger, the BOD, in the hardware that would switch off all the detectors. In addition, presence of an ultra bright source near the UVIT field of view will scatter excessive radiation beyond the allowed limit. The Viz channel is primarily used for the spacecraft tracking. So it is the proposer's responsibility to ensure smooth tracking during their proposed observation. Hence, the proposers need to exercise extra caution in preparing a proposal for UVIT observation. Hence, it is strongly recommended that the proposer follow the guidelines described in email in the documents. In the document, mandatory checks to be done for UVIT observation, which is available at the UVIT webpage at the IIA, and the proposers page on the ASSC website. As I said, this output of WIS filter checking tools is mandatory for UVIT observations. And again, here's a link. Then one can use this tool. So first one can install using this command, pip install CAN-UVIT in the terminal in their local machine. And using this command, CAN-UVIT -H, this is the output one will get. It shows the different flags options available for the tool. Here -R is for the right ascension of the coordinate, and the format is also specified here. And -D is for the declination angle of the target of interest, and -I is for the instrument, and -H is for the help. So next I took the test case. So I gave the array for of this and declination angle of this using this command CAN-UVIT, and this is the terminal output I'm showing I got for these specifications. So this tools gives bright sources in the field of view of UVIT instrument, and the first line is the array, and the second one, I mean the column. The second column is for, the declination angle of the sources which are in the field of view of the UVIT. The third one is the magnitude. The fourth one is the V minus V index. These are the spectral types of the sources, and these are the count rates in the different filters of WIS channel. So for WIS channel, if the count rate is less than 4,000, then it is expected to be safe. The source is expected to be safe to be observed with this channel. So as we can see in this particular case, the count rates are less than 4,000, and so the output we get over here is that the safe filters are all these 5. Then this single tool can be used to get the output for FUV and so for NUV, these are the RA and DEC, magnitude, corrected magnitude, and these are the count rates for different silica B4, B13, B15, and N2 filters. For NUV and FUV, if the count rate is less than 1500, then it is assumed to be safe. Yeah, somebody has raised hand. Should I stop?
Please go ahead. We will discuss later. I mean, after your presentation is over.
Yeah, should I can't hear actually.
Hello. Divya, please go ahead.
Okay. So okay. So same for the yeah, as I said, for NUV, if the count rate is less than 1500, then it is assumed to be safe for the NUV filter. And as in this particular case, we can see that it shows the output that all the filters are safe for NUV. Then for okay, yeah. So the UVIT 20 arc minute field of view can have potential bright sources, the BOD, and in case of BOD, the UVIT will go into a switch off mode. Also, if selection of filter is not done properly, the proposer may get rejected. As Yashpal have already mentioned, these are offsets between, there are offsets between the different instrument. So if due to these relative offset, if we have chosen the primary instrument as ASSC, then the search radius will be 25 arc minute around the target of interest. And if one has chosen the primary instrument as LXPC, the search radius will be 28 arc minute around the target of interest. Yes, this I have already mentioned. So here too, okay, in the case of FUV2, we can see that the count rates, these are the count rates for the filters CF2, BF2, Sapphire, and Silica. These are all less than 1500. So the output is that all the filters are safe for FUV. So next I used the test case of the galactic microquasar source GRS 1915 and gave the RA index accordingly and chose the primary instrument as A60, and here's the output, terminal output I got. So for this channel, these are the RA index of the sources in the field of view, and this is the magnitude, this is a B minus V index, spectral type, and these are the count rates. So for this source, the count rate is greater than 4000 for this channel, WIS2, WIS1, and DK7. So the output one will get here is that the filter is safe for ND1. Sorry, the observation can be taken. Yeah, it's safe. Plus also it gives the warning that there exists two pair of bright stars which are closer than 10 arc second. There are special cases for UVIT, FUV, and NUV filter checking tool, which has been already discussed in the last year webinar for A11 cycle, and which was conducted by Jayashree and Shah Alam, and link to those slides or videos is here, and again is available on the ASSC too. Next is the UVIT exposure time calculator, and here is the link for the same. The UVIT exposure time calculator can be used to estimate required exposure time for an astronomical source. The exposure time calculator calculates the expected count rate for a source in various UVIT filters, followed by either the signal to noise ratio achieved for a given exposure time or the time required to reach a given SNR. And the input here required is the type of the object one is proposing, the coordinates on area and depth, and the galactic extinction parameters, and the dark count rate, the background count rate. And depending upon the choice, the output one will get here is either the signal to noise ratio or the exposure time. So let's see the first case when one will choose the object to be a star. For a star, the proposer has to specify the spectral type. The star's spectral type is required to estimate the source flux density at the instrument. The user can use a combination using the 3 drop down list for spectral types and subclasses. Other inputs are flux density and the magnitude here. Then the second case, when the source is a black body. So astronomers often come across sources that can be approximated as a black body. Spectrum of a black body radiation is provided by Planck's law of radiation. The temperature of the black body will decide the shape of the spectrum in this case. And this spectrum is then normalized and flux is scaled to match the source magnitude or flux density. The allowed range for this parameter is from 0 to 10 to raise the power 8 Kelvin. and the type should be either float or the integer. Next is the galaxy and the AGNs. So if the source is a galaxy, then this tool uses a template spectrum and scale it accordingly to the magnitude of the source. It also shifts the spectra to account for the redshift of the source. So 2 or more input parameters are required. That is the type of the galaxy and the redshift. Similar to the case of galaxy, in AGNs too, this tool uses a template spectra to generate the source spectrum. The magnitude of the source is needed to scale the template spectrum. In addition, the redshift is used to shift the profile and wavelength. For example, in AGNs, there are 4 templates that are available: the liner, CFUT1, CFUT2, and QSO. The liner template is basically the spectrum of M81, and the CFUT2 template is a spectrum of NGC 5548. Then the 2 cases, the power law and the flat spectrum. This source parameter can be used, the power law one, to generate a power law source spectrum. In this case, the flux is proportional to lambda to the power A. Here A is the power law index. The source spectrum is then scaled to match the source magnitude or flux density. Next is the flat spectrum. If a proposer knows a flat spectrum source and would like to observe it using UVIT, then this source parameter can be chosen as a flat spectrum. A flat spectrum means one constant value for a flux density at all wavelengths. Then the last option is user defined. If one is not happy with any of the listed sources and want to propose a user defined source, then an option is available where one can upload the spectra of the source. The proposer can also check the redshift option to apply a redshift to the target of the interest spectrum with the magnitude flux option. The spectrum can be also normalized and scale it to given magnitude flux. The exposure time calculator expects a 2-column ASCII file as a source spectrum. The first one is the wavelength and second is the flux density. And it's in the units of erg per second per centimeter square per angstrom, and wavelength is in the units of angstrom. And any line which will start from a hash will be considered or taken as a comment line. Yeah. One can also give name of the source as input. So one has to provide the RA index of the source here, and one can also provide the name of the source. This tool will also give warning in case of sources too close to the galactic plane. Then the other parameters are the extinction parameter, and to calculate the galactic extinction, these relationships will be used. And there are 4 inputs which one can provide: the E, B minus B, the NH, distance, and the ANU, which is the extinction in the B band. And the NH has to be in the units of 10 to raise the power 21 per centimeter square, and the allowed range of NH is around 10 to raise the power -5 to 10 to raise the power 4. Then the last parameter is the background count rate, the normal value for which is around 25 counts per second, which is detector noise. But if a proposer is interested in considering the external contribution, then one can provide the larger or the higher values. As I said, the output will be either signal to noise ratio or the exposure time. Here I'm taking the test case of a galaxy M33. Given the input type as spiral SC and redshift as 0.00597, magnitude as 5.28, RA index of the source in the specified format. The EB minus V as 0.114, dark count rate I'm keeping the same, 25. So this is the output I get here from this tool. So for this band, as it gives a warning that the source is too bright for these two filters. And this is the exposure time required to achieve the desired signal to noise ratio. Then the AstroSat WebPIMS. This tool is useful to get an approximate value of count rate with AstroSat instruments ASSC, LXPC, CZTI, and SSM, provided one should have the prior knowledge of some parameters with other instruments like XMM, Newton, RXT, and etc. This is a link to the tool. So the link will be direct you to here, where these are the inputs from the source. Okay, so one has to select the instrument for which one has the prior knowledge, and the input energy range of the instrument, then the selected instrument for which one is desiring to get the count rate or the flux value, and the energy range for the same, and the flux count rates, redshift, galactic extinction parameter NH, and power law index. So for example, I chose XMM Newton PN thin count rate 15 region as an input in this field. And given the input energy range as 4 to 10 kV, then I want to calculate the count rate for the AstroSat LXPC in the energy range 3 to 80. So these are the counts and the galactic extinction parameter, the power law index, and this is the output I get from the instrument XMM PN thin to instrument AstroSat LXPC, the input energy range, output energy range, and the expected count rate in the LXPC for the given source, the NH which I gave, and power law is the input parameter. So it says that for power law model with photon index this and NH this, and this counts in XMM, the expected count in the AstroSat LXPC, it predicts that it's around 2.5 into 10 to the power 2 counts per second with LXPC 20 in the 3 to 80 kV band. Then the last one, the UVIT 9-point coordinate generator, which check for the bright sources that may be harmful for the UVIT observations. It scans the 9-point around the desired target, and that's how it looks like. Only 3 inputs are required: the target name, RA, and DEC. So I took the test case of GRS 1915, provided the RA and DEC, and this is the output I got. It scans the nearby field, and these are the 9-point coordinate generators. It generates the 9 points around the source field. The downloadable script for the same is also available. So one can first download and unzip the code using this command. Then one can use the Python to invoke it. Okay, here is the terminal output. So again, I took the test case of GRS 1915, and I gave this Python in Python 2 UVIT 9PT, and provided the target name without space and RA and DEC in the specified format, and it generates a TXT file where all the 9 points are listed. So yeah, that's it.
So I would like to thank you, Dr. Divya Rawat and Dr. Yashpal Bhulla for the presentations. Now I request all the participants to raise their hand for questions if they have any questions regarding to proposal preparation for the AO phase 12 cycle.
Hi Divya. I have two quick questions. One of them is like, let's say if I have, let's say if I'm doing UVIT observation and I get that the brights like this, what do you call this, the output for the exposure time calculator, in the visual band, I'm getting all of them too bright. Can the source still be observed? So if I'm looking at a relatively, in the NUV and FUV, it's okay, but in the visual, it says it's too bright. So will that matter if I'm, let's say, if I only want the FUV flux from this particular target? Is that a necessity that it has to be even visible in the optical, or like less bright in the optical as well? Hello, am I audible? Did you guys hear me?
Yes, yes, you are audible.
Yeah.
So actually, you have to configure VIS, and if there is a filter issue, then you have to make sure that it is not bright. I mean, if it is bright, then it is not suitable for UVIT observation.
Like there is no issue in the, like if you look at the bright source warning, that time there's no issue. But if I give it this, if I do the exposure time calculator, it's showing that it's too bright in the visual filters. But I only want
Too
the
bright in the sense whether it is like a bright, it's a warning is there, or it is just brighter as a comparative statement. I mean, like
no, it says too bright, and then there is a, that's it. When you do the exposure time calculator. So Divya also showed like some of the filters that she showed were too bright. So I'm getting
yes.
all the visual filters to be too bright. So is there a way of let's say negotiating with that, or is it impossible to then do this observation?
If there is a bright source warning, then it is not advisable to observe with UVIT as like the for the particular observation. So Gulab can kindly suggest if it is.
Yeah, so in this case, of course, the WIS channel configuration is one of the requirement. But in principle, the FUV data can be used because that's a photon counting data for taking corrections, provided that you have sufficient bright sources to do that, and there are tools. See, in the UV pipeline, I think the NUV was being used for the taking correction, but NUV is no longer available. So I'm not very much sure whether there is a ready-made tool to correct the FUV data. I mean, in the CCD lab, it is there. One can use the self-correction, but that requires bright sources in the central region, and finding several bright sources, or at least a few bright sources in the FUV is sometimes tough. If you, I think you can put a proposal, but you will need to make a careful justification of this. Okay, so all these sources are bright, but how, whether there are at least couple of FUV bright sources in the central region, which will be detectable in 3-4 seconds or 5 seconds. Okay. If you demonstrate that, you will then you will need to find out the point sources. Are they stars in the UV field and particularly close to the center? And then so that every 4 or 5 seconds or even 10 seconds, let's say whatever number of seconds, these sources will be detectable in the FUV, and one can determine the positions and do the correction.
Okay. My second question, Gulab,
Yeah.
I think it's best suited to you. So we are trying to do a spectroscopic observation with UVIT using GRISMs. So you know me and Prashanta have been doing this for quite some time now. So so like if I do the exposure time calculation, it gives me like something like 100 seconds exposure for FUV. But from our experience, we know that this 100-second, at least for spectroscopy, there has to be a fudge factor involved with this. So do you have a sense of what kind of a fudge factor do we need to put?
Yeah, so first of all, because the grading effective areas are there in the calibration paper, you can use that grading calibration area and certain wavelength, let's say 1500 angstrom, given the effective area and given the your flux, how many count rate, what is the count rate you will detect, and then at that wavelength, what is the signal to noise you desire for your science. Depending on that, you calculate, estimate the exposure time and put the proposal for that.
Okay.
Which is not a first factor, but you can calculate for a required signal to noise, what will be what is the estimated exposure time.
Okay, so we shouldn't go by the exposure time listed here.
Yes, that's not meant for gratings.
Okay. Okay, thank you.
I had a comment about your previous question regarding very bright visible source in the field of view. And if even with the neutral density filters, you are finding the object to be too bright, then this is actually a rare kind of object. And so it is possible that this object is not exactly very close to your desired source. So in that case, you can try to do an offset pointing where your desired source is not at the center of the field, but it is somewhat away, but your bright source is completely out of the field. That is another possibility you can try.
Yeah, this is a very good suggestion, given that UV field is pretty large. So if you can avoid that bright source, that would be a very good thing to do, because UV field within the 40 arc minute, let's say if the source is within the 30 arc minute diameter circular region, then your PSF is still good and you can study the source very well.
Habib, please ask your question.
Yeah, hi. So suppose we go for an anticipated TO, and suppose there are some trigger from other telescopes. So how much is the minimum time required for AstroSat to respond to that TO?
So if you submit an anticipated TO proposal and if that is accepted, then it is your responsibility to request for a trigger. So you will need to monitor other feasibilities for the triggering criteria to satisfy. Then in APPS, there is a provision where you will log in and submit that trigger request by justifying whatever is the source and your trigger criteria, whatever is you have given as that the trigger criteria has now been met. That will be looked at by the ATEC chair and that will be approved. So that typically will be approved within a day or so. I wouldn't imagine, because that's only ATEC chair looks at and checks what is the trigger criteria in your original proposal and your justification, and approves or disapproves depending on the thing.
Okay.
Yeah, then there will be scheduling overhead. So
yes,
typically the fastest you can expect is about 2 days, but sometimes it can be longer depending on what observation is going on, whether that can be interrupted or not.
Yeah.
Okay. Thank you.
Yes, Minerva, you can ask your question.
Hello. Well, my first question is, well, no, it's not a question. Could you please share the link to download CanUVit? Because I tried to find the filter of the visible wavelength, but I couldn't because
Okay,
the page
actually,
is
yeah, thank you, Minerva. This application, the CanUVit, is available in ASSC website for proposals page, where you get all the other tools available. So if you click for the filter selection with FUV, NUV, or this VIS, you will get the link to this particular application.
Jayashree, you can share and show the link.
Okay.
Okay, well,
yeah, I have shared the link.
The second question is, which is the average exposure time? I got, I saw in the previous presentation that it is about 1 second. Is it normal?
Sorry, Minerva, I could not understand.
I wanted to know which is the for a galaxy, which is the average time exposure.
Average exposure time, for a typical galaxy.
Is it not?
They're about it will be about a kilosecond. You're looking for FUV observations, right?
Okay.
Yeah.
And yes.
Typically a kilosecond. Something like 1 orbit or will be the minimum.
Okay. And the last is that in the page where I submit my application, you ask for the flux in between 2 and 10 kilo electron volts. But I wanted to know which flux should I integrate, the one given by Galax or the one in the visible?
2 to 10 kilo electron volt, it is in X-rays, right? So if you have any information in X-rays, then you fill it. If you don't have any information regarding X-rays, then you just put 0 over there.
Okay, thank you. Thanks.
So we have shared the link of CanUVit in the chat box for everyone. The links are referring to the AstroSat proposal preparation page and the locations with UVIT VIS filter checking tool and UVIT FUV NUV filter checking tool. Thank you.
I just want to make a comment regarding the earlier question regarding this the bright all bright wish sources, whether we can do if all these wish sources are bright, and if one is requesting for FUV observations in the imaging mode in one of the broadband filter, then it may be possible provided there are bright FUV sources in the field. But if one is going for grating observations without the wish sources available for tracking, then it is almost impossible to correct, because unless someone writes a new tool, because unlike the broadband images, the grating will have the arms, they are not point sources, while the tracking tools require the point sources. So that becomes extremely tricky and almost impossible to do that. That one should keep in mind.
Grating observations are not recommended without this support.
Yes, yes.
So
currently there is no tool.
So are there any more questions? Kindly raise hand. So just for the information, all these video recordings will be available in the ASSC web page, that is AstroSat Science Support Cell web page, for future references. So if there are other questions which you remember in the due course, or if you want to ask, you can also write to AstroSat Help. Okay, it seems there are no questions currently. So I think like we will receive questions in AstroSat Health. So with that, we would like to close the webinar session for today, and I would like to thank Dr. Divya Rawat and Yashpal Bhulla for the presentations, Professor Deepankar Bhattacharya and Professor Gulab Devangan for helping with the question answer discussion session. Thank you very much. So I would like to thank all the participants.
Yeah, thank you. We look forward to excellent proposals this time. So please do submit.
Yes. Thank you.
Thank you.
Bye.
Thank you, everyone.
Bye.